Vapor pressure and change of state. Remember, vapor pressure is the pressure pushing up from the surface of a liquid as it becomes a vapor. This picture here shows, in part A, those molecules that are leaving the liquid to become a vapor. They've obviously gained enough energy, overcome the intermolecular force to become a gas. And you can see that at some point in this closed container, this is letter B, that the number of molecules becoming a vapor are equal to those that are leaving the vaporized state and becoming a liquid once again. These would be kind of in equilibrium, and initially, and then at equilibrium. Had I pushed that button, we would have seen that sooner, but at least we know what it is. So, at equilibrium, the rate of evaporation and the rate of condensation happen at the same time. And you can see by this graph that relationship. So what is vapor pressure, and how does that interact with the change of state? Pressure of the vapor present at equilibrium. The system is at equilibrium when no net change occurs in the amount of liquid or vapor because the two opposite processes exactly balance each other out. And of course that's what equilibrium is, two things happening in the opposite direction. So what is the vapor pressure of water at 100 degrees? How do you know? Well, remember, at 100 degrees, that's the normal boiling point of water. When the vapor pressure equals the atmospheric pressure, that's boiling. So when those two processes are happening at the same time, boiling is happening. So under normal conditions, water will boil at 100 degrees. So the vapor pressure there must be standard pressure, or 1 atmosphere, 760 millimeters of mercury, or 101.3 kilopascals. That's how we know. Let's see what they say. 1 atmosphere. We were right. So let's take a look here at different pressures. Remember, the pressure of the vapor is that which pushes down on the surface of this dish of mercury from the atmosphere. So that's atmospheric pressure in a barometer. This is a simple barometer. And you can see on the average the pressure of the atmosphere is 760 torr. Different substances have different pressures, and it will change the amount that particular column of mercury can be pushed up. Liquids in which the intermolecular forces are strong have fairly low vapor pressures. They do not become a vapor easily because they stay in the liquid state. Vapor pressure increases with temperature. So as temperature increases, the energy given to those molecules increases, and those molecules can become a vapor easily. Vapor pressure versus temperature. If we look at this, we can see that the vapor pressure is graphed here on the y and temperature is on the x. 760 torr is standard. Now at standard pressure, it looks like dimethyl ether will boil at 34.6 degrees. Ethanol will boil at 74.8, and water will boil at 100. Water is the only one of those three substances that happens to have hydrogen bonding, which is a relatively strong intermolecular force. Now, what are we going to look at next? Again, vapor pressure. Well, sometimes we have to calculate vapor pressure, and we can use the Clausius-Clapeyron equation to do that. Here's the equation. Oh, you say, look at how exciting that is. I can finally use my natural log skills. Well, don't get too excited because, of course, in chemistry, you're just going to be using your calculator. But what does all of this mean? Well, P vape is the vapor pressure at temperature 1. Notice it says T1 in the numerator and T2 in the denominator. Delta H vaporization is the enthalpy of vaporization. Delta H, or heat of reaction, is a given number. We will, again, later in the year, when we talk about delta H, delta S, and delta G, review delta H. But for now, we're going to have to take it as given. R is the gas law constant, 8.3145 joules per Kelvin mole. Now, back when we learned the gas laws again, PV equals nRT, sometimes you can use different values of R. You can get away with it and it's fine. It's just as long as the pressure and the value of R are in sync with each other. However, in the Clausius-Clapeyron equation, we really want to use R as 8.3145. And so that's why when I was back in high school, I only memorized 8.3145 because that's the value of R we tend to use over and over again for different situations outside the gas laws. And of course, T is temperature. T1 is temperature 1, and T2 is temperature number 2. And usually you're solving for something like the vapor pressure at a temperature that you're not given. So let's see if they give you a question. Yep, here you go. The vapor pressure of water at 25 degrees is 23.8 torr. And the heat of vaporization of water at 25 is 43.9 kilojoules per mole. Calculate the vapor pressure of water at 65. All right, so what are you going to do? Well, you're going to have to plug into the Clausius-Clapeyron equation. So for that, you're going to say Ln, and we're going to say pressure of the vapor at temperature 1 over pressure at temperature 2 equals delta H vaporization over R 1 over T2 minus 1 over T1. Alright, and then it's just a matter of plugging in. Now, the pressure at temperature number 1, I'm going to say temperature number 1 is 25. So I'm going to have Ln of the pressure is 23.8 torr. I do not know the pressure of the vapor of T2 because I think, yep, that's what we're trying to solve for. So we got to have one variable. The delta H of vaporization, well, they tell me it's 43.9 kilojoules per mole, which is perfectly fine. But you'll notice, on the previous slide that is, the value of R is in terms of joules. So I have to change this numerator, delta H, to 43,900 because it has to be in terms of joules per mole. And then I use 8.3145. Now obviously I could switch that, 8.3145, or I could switch the other, but they do have to be in agreement. Alright, and then 1 over T2 minus 1 over T1. T1, remember, was 25 degrees. So it's 25 plus 273, whatever that is. And this is 65 plus 273. Obviously, we do that in the calculator. And then using, would resolve the right-hand side, I get a number. And then I'd have to actually take, it looks like the anti-log of both sides to try to solve for pressure of vapor. And let's see what you get. I didn't do it, but that's how you would plug it in. According to this PowerPoint, you get 194 torr. So again, remember, you have to use the anti-log or the inverse log. It depends on your calculator. Hopefully you too will get 194 torr when you work that out. What else can we look at about vapor pressure and change of state? Well, here we have a heating curve for water. Remember, there are three phases: solid, liquid, and gas. In a phase change diagram that you see like this one, a temperature, a heating curve, very common kind of curve, you can see there are 5 segments. This segment number 1, 2, 3, 4, and 5. I guess you could say those are the 5 segments. Let me erase that. Or maybe I'll stick them over here. 1, 2, 3, 4, 5. 3 of the segments, this one, and this one, are slanted. 2 of the segments are plateau or flat. During the flat segments, we have a change of phase. And the thing to remember is the temperature is constant. So during a temperature change, during the phase change, the temperature doesn't change because the energy, the added energy, goes into overcoming the attractive forces to become another phase of matter. The other 3 phases of matter, these slanty regions right here, are temperature changes. And the phase remains constant. So either you have a temperature change or a phase change, but you can't have both at the same time. So you notice at the bottom here you have ice, and then you have water, and then you have steam. During the phase change, you have 2 phases of matter, ice and water and steam. And you can see, if you look carefully, the ice and water happen at 0, and the water and steam happen at 100 degrees. So these are just examples of heating water. Again, those substances endothermic have to take in energy to produce the steam.